Hi, everybody. Welcome back to Dave's Math channel. This is my next video on my series on the Math Lovers book. I'm now up to section 2.7 of volume 1. That's the volume shown on the slide on the left. And I'm not going to bother advertising my Math Lovers book anymore. Just suffice it to say, there's three volumes in the series, and you can buy them on Amazon.com. And that's all I'm going to say about it. But I'm going over the first volume, which is the more recreational one. I'm on chapter 2, which is on numbers. And today I'm going to talk about, I'm starting a new section on very large numbers. And today I'm going to talk about names of large numbers. So let's begin. Um, so, yeah, so you might be surprised to know that there's a standard nomenclature for names of numbers with up to 305 digits. Really, really big numbers. You might be surprised to know that. And I'm going to explain the system. Without further ado, here's names of numbers with given number of digits up to 303 digits, and you're probably familiar with the first few of these. I mean, the first number with these are zeros, by the way, not digits. So the smallest number with no zeros is one, or I'm talking about positive numbers now. And then, if you want to add another zero, you get 10, and then 100, and then 1,000. There's a different name for numbers where you multiply by powers of 10 up to 1,000. Then you got 10,000, 100,000, a million. I'm sure you guys learned all this when you were in grade school. But then we go up by factors of 1,000, and we give the numbers different names, starting with a million. So million's first number was six zeros. Billion is the first number with nine zeros. And there is kind of a logic to this. Million, MI, is Latin for one, me. So you kind of add illion, the suffix illion, and then you start with a Latin prefix for numbers 1 up to, I guess 1 up to 100, actually. So MI is Latin for one, so the first number with six zeros. And since we used 1,000 for the first number with three zeros, we start a million with the first number with, 3 plus 3, 6 zeros. And then we keep going up by thousands. It's not a really great convention, but this is what we all use. So the first number with six digits is a million, first number with nine digits is a billion, then with 12 digits is a trillion. You guys probably hardly ever see numbers bigger than a trillion used, at least with a name. But there are names for bigger numbers. When you get up to 15 digits, you got a quadrillion. Then you got a quintillion with 18 digits, sextillion, 21 digits, septillion, 24 digits, octillion, 27 digits, nonillion, 30 digits, and decillion, 33 digits. I actually learned these names when I was in second grade. I used to have a book, called Zero to Zillions. I don't know how many guys have heard of that book, but I think my grandma gave me that book when I was like in first or second grade because I was a math prodigy and she knew it, and she thought she'd give me an entertaining book, a kind of an advanced book for little kids. And so I learned the names of all the numbers up to a decillion when I was in second grade. I just want to say one more thing about this. The estimated number of elementary particles in the observable universe is about 10 to the 89. I mean, if you don't include photons, it's about 10 to the 80. There's about 10 to the 80 elementary particles of matter in the universe. I'm going to talk about scientific notation tomorrow, I think. But 10 to the 80, that's the smallest number with 80 zeros. And that's even smaller than well, no, it's actually bigger than a decillion. It's it's a lot smaller than a Google, but that's almost like the largest physically realizable number. Of course, it's not because you can have combinations of objects. Combinatorics involves really really huge numbers, and we don't even use names for those numbers. But if you're just talking about counting things, I don't think you're ever going to have to count bigger than 10 to the 89 because that's the number of elementary particles in the observable universe. And there's nothing else you want to count, at least physical. Maybe you can count abstract things if you can think of them. But anyway, just thought I'd mention that. And then beyond decillion, we have to use Latin names for things bigger than 10. So then we got undecillion, I don't even know how to pronounce that. And duodecillion, tridecillion, quatordecillion, quindecillion, sexdecillion, sept. I never use these things. I have to read them. Um, yeah, septendecillion, octodecillion, novemdecillion, vigintillion. Now we're up to 63 zeros. And then after that, then you can kind of, it's almost like when you're counting like 21, 22, 23. So I guess the first number with 66 zeros would be unvagintillion, because we're using um, the Latin prefixes for the numbers 1 through 9. You have duovigintillion, trivigintillion. I think you get the idea. And you keep going like that, and then you get to trigintillion, which has 93 zeros. And then, might as well just skip each multiple of 30 zeros now. So quadragentillion has 123 zeros. Then quinquagintillion, these are weird names. Sexagentillion has 183 zeros. Septingentillion, 213. Octogentillion, 243. Nonagentillion, 273 zeros. Finally, the largest number with a name. It's not quite true, but the largest number with a simple name is centillion, and that has 303 zeros. And cent is the Latin prefix for 100. And using this system, you can actually get numbers with up to, I think, 300 and what is it, 305 digits, I think, or maybe 306. So the largest number in the system would be something like 999 centillion, and then you can keep going. You keep adding the prefixes. I don't think anybody really uses these numbers anyway, but they do exist. And there's just one more thing I want to say before I get off of this. You guys probably know about the number Google, or a Google. I think even the company Google was named after this, although they spell it differently. The number Google is spelled Googol, and then the company Google is spelled Google. I'm not sure why they spelled it differently. But Google is already more than the number of elementary particles in the observable universe. Google is a huge number. Hardly ever see it used. But and then you got even bigger numbers than Google. You also have a thing called a Googleplex. There's this plex system where I guess plex is the number of zeros. So Googleplex would be the smallest number with a Google zeros. In other words, 10 to the Google's power. Yeah, that's kind of unimaginable. I have seen bigger numbers this used in math, though, by the way. There's a number called Skewey's number that used to be the biggest number that was ever featured in a math paper. I think it was John Littlewood, if I'm not mistaken. He estimated, where this prime counting function, the first place where it superseded the natural the logarithmic integral, which was he estimated he came up with an upper bound for that number about 10 to the 10 to the 10 to the 34th power. Some of these numbers are so big, if you try to imagine them, your head would explode. But and there's even bigger numbers than that. I think the biggest number that anybody's ever used now in a math paper, if not for saved, there's this function called the tree function, and I've heard tree 3 is like just an unimaginably large number. Before that, I think the record was Graham's number. And there's this arrow notation that Graham came up with. This is not in my book, by the way. There's two kind of famous notations for just unimaginably large numbers. One of them is due to who was it? Really famous. Donald Knuth. Donald Knuth came up with arrow notation, which is used to represent Graham's number, which is an unimaginably large number. I'm even going to try to describe. But there's another system where you put kind of polygons, regular polygons around numbers. And this is, I think, a system. I don't remember who came up with a system. I think it was Moser. There's a number called a Moser. And I don't think it's even known whether Graham's number of the Moser is bigger because they use different systems to represent them. but they're both just unimaginably large number. Like I said, if you try to imagine these numbers, your head would literally explode. Your head can't retain that much information in it to even comprehend these numbers I'm talking about. But at least the numbers on this table aren't that big. I mean, they're pretty big, but you can imagine them. I mean, you can write them down. You can write them down. All these numbers you can write down on a single piece of paper. So, I've seen bigger numbers than this, and I've seen estimates of pi. I think I even once calculated pi to 1,000,000 digits from Mathematica, which it did in about a minute. And 1,000,000 digits is so many digits it would take a whole book to print them out. But I printed them out on a spreadsheet. It was a huge spreadsheet, and I deleted it pretty quickly because I didn't want to hold on to a huge spreadsheet. But anyway, that's large numbers for you. So that concludes my video for today on very large numbers. And thank you for watching. And long live math, and I'll see you guys next time. Bye.